Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to look at the logistic equation, and harvesting. So, what does that imply? The logistic equation is actually often used as a representation for the way a population grows and declines in an environment. So let's take a look at our problem. We've used this example and we'll use it again. Y prime equals 3 times y minus y squared. So I'm going to sketch this graph here. I'm going to pull up some graph paper for a moment to do this with. So let's see. Okay. There's my basic graph. Remember, we had t on the horizontal axis and y on the vertical axis, or y of t. And in this case, we said that we have at 3, and at 0, we had our derivative is 0. I'll just put a dotted line here on the y-axis, or the t-axis as well. And what we said was this. We said right in between them, right in between these two, at 1.5, so there's 2, 1. Right at 1.5, we have an inflection point. And our general graphs looked like this. They looked like what they would do is maybe if a graph started, I don't know, maybe it started at half, well, the population would grow and be concave up, and then what would happen is once you pass your inflection point, the derivative still stays positive, the growth continues, but it reaches a ceiling. So let's just take a look at the S-curve. That's what this is called. This is called the S-curve. And what this represents is a population would grow and then it begins to decline. You might think of fish in a pond. If the pond had no fish and someone put a couple fish in, well, they'd have the whole lake. There's tons of food. The fish would just grow and the population would expand, and probably at a fairly fast rate. But all of a sudden, the point at which the fish grow would very quickly start to slow down because there's not much more space. They're at a balancing point where there's no more food, so the population reaches a steady state. Another example was actually the introduction of cell phones. Initially, very few people had cell phones. They were expensive, and there wasn't a big network in place, so the growth was very low. It started out the curve might have been shifted, like maybe it started out very slow, almost imperceptible growth. And then what happened? They got better at making them. They got better. They had the smartphone, the iPhones, and then the Android phones, and it just took off. Well, what happened? The cell phone use just grew like crazy, but then it kind of capped. Once the market's kind of now saturated. I mean, sure, there's probably more people out there that need to buy cell phones and will, but the number of cell phones is probably that the number of cell phones in the world, or people that need to buy one, kind of reaches a more moderate pace. So that's what we expect. There's a cap. Now, what happens if our fish get too many in the pond? What happens if we get like 4 fish in the pond? Well, then we said the derivative was 0, and it comes back down. It comes right back down to this stable, this is a steady state. So that's what this is a steady state. So the logistic equation is really trying to, it models the steady behavior of growth, mostly of a population. Now you might say, well, what happens though below? Does this even make sense? Well, what happened below is, remember, if we got just even the fraction below 0, then this declines very rapidly. It almost just falls off if you were to graph it. and we can figure out where that point is, but it just immediately approaches a vertical asymptote. So if you get below this critical unstable state here, this is unstable state. It's not just a little unstable. It's like it's going to rocket out of control unstable. Let's take a look. I want to continue with my problem, and let's imagine for a moment that we have a lake. Here's my lake. And in this lake, there's some schools of fish. We'll call it, we have school number 1, maybe they tend to stay over in this part of the lake. Then there's school 2 over here. They tend to stay in this part of the lake. And then there's a smaller school of fish. We'll call this one school number 3. Okay. Actually, maybe school 2 stays. School 1 and school 3 stay at opposite ends, and then school 2 stays out in the deep water. They like the deep, cool waters of the lake. Now, what happens if we harvested about 2 of these schools of fish each year? Well, what happens if, and I want to show us a few ways. So we're going to harvest 2 schools of fish each year. 2 schools of fish each year. All right, so how do we represent that? We represent that with the logistic equation of y prime equals 3y minus y squared, and we're going to just take 2 of those off each year. Okay, before we continue, I want to make one more graph. Let's do this. Here's my next graph. And on this graph, we need to do a little more notation, is we're going to plot y on the horizontal axis and f of y on the vertical axis. Now recall, the f of y is just another way of identifying y prime in this autonomous equation. So let's graph. I'm going to call this the first f of y. We'll call this f naught for no harvesting. And then this next one that I've written down, we'll call this f2 of y because we're harvesting 2 fish. So let's graph f naught. We'll do that in blue. Well, that's this parabola. So let's just say this is the parabola. If I factor this out, this is minus y squared minus 3y, and I'm going to put it in its vertex form. So if I want to do that, I need to complete the square. So I take half of minus 3, that's 3 halves. I square it, that's 9/4. And so I'm going to add 9/4. I'm going to subtract 9/4 times the -1. So minus 9/4 because I added, but I have to remember that -1 out in front. So -1. So effectively, we're adding 9/4. So this is, in vertex form, minus y minus 3 over 2 squared, oops, that's a -1, plus 9/4. All right, let's graph that down here. So I'm going to call this 1, 2. I'm making a kind of a big scale just for clarity. And let's go up here. We'll go 1, 2, 3. So I have a vertex at 1.5, 2 1/4. Well, 2 1/4 is probably like right about there. 1.5 is right there. And you can just look at that, and we already know that it's 0 at 3. Let's do a different color for this. It's 0 at 3, and it's 0 at 0. So I have this parabola that's shaped like this. Okay, so this is f0 of y. Okay, now that we harvested 2 fish, let's see what's happening to our picture. Well, let's complete this square over here. I'm gonna write this as a, let's go back to our other color here. Let's go minus, we have a y squared minus 3y minus a 2, and then we're going to add 9/4. And we already said that that works out to adding another 9/4. So we could think of this as minus y minus 3/2 squared. This is going to be plus 1/4. Whoa, hold on, a few things to keep in mind here. Here's one of them. Notice that the vertex of the parabola, the vertical axis of the parabola is also the same as the inflection point in my graph. And that by harvesting, notice that the inflection point doesn't change. But what does change are the zeros. When is f2 of y equal to, which is, let me write it out. I'm going to write it as a minus y squared plus 3y minus 2 equal 0. Where are the zeros in this picture? I'm going to multiply by negative once to solve this. So y squared minus 3y plus 2 is still 0. If I factor, this factors into y minus 2, y minus 1 equals 0. And so now this says that y equals 2 and 1. Whoa. So now my new parabola has a vertex at 1.5 comma a quarter. So comma a quarter. Whoa, that's way low. That's so low that we should probably do another color so we don't lose track of it. It might just disappear off the bottom of my screen. Okay. And it has zeros at 1 and at 2. Oh my gosh, it's the exact same parabola, but look at how far down it has been pushed. It's been pushed all the way down like this now. My, that's a big change. Well, what is happening? So my parabola is getting negative. And notice that it matches up. For example, the parabola, when it's negative, like when it's down here, for values greater than 3, it has a negative slope. And we represented that up above by this graph up here. Okay, now I'm going to come up with a totally bolder color. Let's use this kind of brick red color. And now let's make a graph of my new curve. So here are my zeros at 2. I have another 0 here at 1. And now my population is stuck somewhere in here. Look at that. This red curve, this is my f2 of y. Well, what just happened? Well, think about it this way. Let's go back to our pond in the bottom left corner. It says that I'm going to go and I'm going to take each year, I'm going to harvest 2 schools worth of fish to feed my family and maybe to barter. So I harvest 2 schools of fish, but I leave the third group untouched. Well, no, I'm sorry. I don't want to harvest 2. I'm going to harvest, let me do it this way. So I'm going to harvest all of one of these, and then we're going to harvest almost all of this one. So maybe scratch out all of the 2. Then we're going to scratch out almost all of the 1. Well, if I do that, and then I come back to go fishing the next year, what I will have is I won't have 3 schools of fish to harvest from. I'll have just 2. That's the most my pond can grow back to when I'm harvesting 2. So I'll harvest, but if I do that, if I just harvest 2 fish a year, the maximum the population will be 2, and I will be able to keep fishing. However, what happens if I harvest all of those 2, and then I'm like, there's still a few fish down in the west end of the lake. What if I just take a couple little fish out? Just a couple. what's going to happen now is look at our curve. Just by taking a few more fish, my graph of f of y is going to sink even further. It's going to drop. It doesn't take only a quarter of that population. Look at that. Just a quarter more. And my curve is going to drop down below. And what that means is, even though there's still fish, their death rate is going to exceed their birth rate. And your population of fish will not be able to sustain themselves, and they will die out. It's called critical harvest. So once you've gotten your population where it's right here at zero, it's called critical, meaning if nothing happens, if their growth rate, their birth rate remains the same, if there's no other predators that come into the picture, they can at least stay steady. They won't make any more unless something changes, but they won't make any less. But you take one more fish because you were hungry or whatever the reason, then you over-harvest, and you've taken too many fish for the population to ever recover. So I have one more question, and that would be, what is that what is that point at which you're going to break the population? Well, that point would be some harvesting value so that my H is I want to harvest it so that I land right there. So my vertex, I want over harvesting or critical harvest is when the vertex, I'm going to write it up here, the vertex is, in our case, it's going to be 3/2, 0. That's when it's critical. If we go below that, our population is on this bottom curve over here. It is immediately or quickly going to die off. So here's how we can solve that. So I'll call this one FH. What's that magic number? Y. So this is equal, I'm going to write it again, minus, write it as y squared plus minus 3y minus h. Well, we know if we complete the square, we would add 9/4 into here. So we would add 9/4 to here. Oops. And then what we have is minus y minus 3/2 squared minus h plus 9/4. And that critical harvesting occurs when this part of my vertex equals 0. So if I solve minus h plus 9/4 equals 0, in other words, h is 9/4. If I harvest at that many schools of fish in just 1 year, I will wipe out my population. It's a simple model, but it's a surprisingly accurate model. And I remember reading recently in the Wall Street Journal about an area of China that just recently experienced this, and now the population of fish is not coming back, and it's changing villages that have fished for years. Anyway, I hope that helps. Thanks for watching.